So, welcome back, Gail. Oh, sorry. Okay, so all right. So last hour, during the first talk, we saw what lattices are, what lattice problems are. We saw an average case hard problem, the short integer solutions, and we showed how to construct collision-resistant dash functions from it. We showed a worst case to average case reductions. For then, now let's move on. All right, but before I do that, I want to clarify something that came up in this worst case to average case reduction, which is a question by Tal and another one that David somewhere asked. Right, which is that why do I pick a random lattice point and add Gaussian noise to it? Why don't I pick sort of a fixed lattice point, let's say 0, and add a Gaussian? Really, the key reason I do this, believe it or not, is to ensure that the lattice vector that I construct, the short lattice vector I construct, is not a 0 vector. Right? It sounds trivial. This should be the easiest thing to prove, right? But it isn't. This is really the core of the analysis. And the difficulty comes in because of the following. Let's say for a moment that the adversary, right? I mean, the adversary looks at these AIs, this SIS instance, and the AI sort of tells it what these YIs are, right? So because I looked at the YIs, I looked at the coefficients, that's how I constructed this SIS instance. So he kind of knows what these YIs are. And now he thinks, I mean, this guy is a computationally all-powerful guy, right? Because I'm doing a reduction, a black box reduction. So he thinks about it and says, well, let me pick an SIS solution, R1 up to Rm, so that the sum of Ri, Ei is 0. Right? If he can look at Yi and figure out exactly what this Ei is, he can do it. He has all the power in the world. He can potentially do it, and then I'm screwed. I ask him once, he says, I ask him once again, he says 0. Third time, I says 0. Okay, so I somehow want to argue that this cannot happen. And why can this not happen? The key point here is an information theoretic argument. It says that given Yi, this noisy lattice point, there are many possible choices of E sub i's. And what does that mean? It either comes in because I chose a random lattice point, so I could have chose this lattice point and added this error, or I could have chosen this lattice point and added this error, right? I mean, the adversary looks at Yi and he doesn't know what the Ei is, so he cannot screw me over, right? He can sort of make one of the choices evaluate to a 0 lattice point, but not all, right? There's only one point that he can kill. So you somehow have to run this sort of hiding argument, right? Namely, given Yi, there are many possible choices of Ei. This is one way to do it, because I chose many different lattice points. Another way to do it is to say, I'm always going to choose 0 as my lattice point, sample a Gaussian around it, but I don't stop there. I reduce it modulo the parallelepiped. This is exactly like reducing numbers mod other numbers, right? That again ensures that if I give you the reduced number, you don't know where I started from. There are many possible places you could have started from, and that hides information again. So all this is to ensure that the lattice point I reconstruct at the end is not 0. Sounds like a triviality, but this is really absolutely the core of the analysis here. It's actually the core of many things. I mean, it's really what happens in the co-AM protocol for the complement of SVP that I showed you before, the Goldwasser protocol. That's what happens. You take the Aitai Kumar Sivakumar analysis of the 2 to the n time SVP algorithm. That's what happens. All the time you have to argue that the vector you're constructing is not 0, and the argument is something similar to this. Not sure how much this makes sense to you, but the point is you somehow have to hide information from the adversary, and it has to be information theoretic, because I'm doing a reduction. I don't know what the guy does. He could be the god, right? I mean, I don't know. He could solve everything. Yes. Okay, good. All right, so let's move on. We're done with SIS. I want to tell you about another average case problem, which is learning with errors, or LWE. And that is the following problem, right? So here it is. The only thing I did here is I moved the indeterminate, the vector here, from left to right, or right to left. That's all I did. Okay, so now things change drastically, right? So now, instead of being underdetermined, this is an overdetermined system of equations. Right? Another question is, can you find S? Well, you can. I mean, right? Gaussian elimination. If there is an S, you'll find it. If there is no S, you'll detect it, so on and so forth. Everything is easy here. And again, as I did before, let me change the question a little bit. Right? So let's say that I give you S times this matrix. And by the way, this matrix is always public. Right? Like in SIS, this sort of linear equation, which linear equations I'm working with is public. I give you an indeterminate S, which is in my head, times this matrix, plus a small error vector. In other words, like each sort of coefficient of S times A, this matrix, I perturb it by a little bit. Say add a random number from -8 to 8, something like that. Right? So this is a parameter of the problem, and I get this. And now my question is, can you find S out of this? First of all, it's not even clear that the choice of S is unique, right? Because if you choose your parameters in a funky way, there could be many possible sort of solutions to the system. But if you choose it in the right way, namely you don't add too much error here, you get uniqueness, right? If I give you many noisy linear equations with not too much noise, the solution is information theoretically determined. It's unique. And the question is, can you find it in polynomial time? Right? That's LWE. This, again, is hard, believed to be hard. Very hard. I don't know what that is. Okay, so more formally, I have A, which is the same type of matrix as before. It's n by m, so, short, thick, fat matrix. I do S transpose A plus an error, and your goal is to find S. Right? That's learning with errors.
So Vinod, can I ask you a philosophical question? I mean, as I just
philosophy is great. Yeah, good. Yeah.
So some points, like I remember, showing my age, like in the old day of lattices, I was a little bit, because it was not mod Q. It's like this thing over reals. There is like no bounding. So it was kind of unfriendly thing, and suddenly there was the thing where mod Q appeared, and now all crypto guys can use a black box. Everything is friendly. So what is this philosophy? I mean, I know there is this worst case to average case, where this mod Q randomly appears, but to me, it made lattices kind of much friendlier. So I'm just curious, what's your perspective of mod Q kind of coming?
Why did it? So first of all, it makes it easier to argue about a random object, right? So the difference in perspectives was rather than choosing a random lattice point and sort of work with this, what does it mean choose a random lattice point? The way that Mickey and Itai and Dwork handled this is to say, well, let's kind of pick a really large kind of rectangle and choose a random point within this rectangle. Right? So then you have to deal with all sorts of boundary issues. It becomes challenging to analyze it, right? So rather than say that, the new sort of thing in sort of the work of Michancho and Regev is to say, I'm just going to pick, instead of choosing a random lattice point and adding a Gaussian, for instance, in the worst case Trappist case reduction, you pick a point you add the Gaussian to the 0 lattice point. So in some sense, you don't care about random lattice point. It doesn't buy you anything. And reduce it modulo the parallelepiped. So instead of working with the lattice, which is an infinite group, you work with r to the n modulo the lattice, which, I mean, it's not, it's something that you can discretize and you can argue about nicely.
I guess
right, so
one thing could be that you just added some more basis vectors, which is just multiples of Q. Okay, they're like,
Okay, I see. So you're asking.
It just becomes much simpler now because you can do everything mod Q. But essentially, it still remains a lattice problem. All you've done is added multiple more.
So this question of how is SIS a lattice problem and how is LWE a lattice problem? What do they have to do with each other? We'll get back to it. Trust me. In a short while, right? But the best answer I can think of, maybe other people have better answers, is that instead of dealing with sort of the infinite lattice and kind of somehow dealing with boundary issues, you don't have to do that anymore. You still have to deal with these sort of the epsilon nets, right? But it's nicer than the boundary issues. But that brings up actually a very interesting point. So what's happening in LWE is sort of uniqueness, right? So as I said this before, if I give you sufficiently many equations, the solution, even with noise, the solution S is unique. And that, philosophically, is what lets you do something like public key encryption. out of LWE, right? You need uniqueness. If I give you the encryption of a message, it better be that the message is uniquely determined. Injective trapdoor functions, if I give you the output, it better be that the input is uniquely determined. And that's the kind of thing that LWE lets you do. This was done before, actually. So the first sort of public key encryption from lattices was the ITIDE work crypto system, which was based on the worst case hardness of something called the unique shortest vector problem, right? So, which is saying, I have a lattice, I know that the second shortest vector is much larger than the first shortest vector, so there's a gap between the two. Can you find? Right? So the promise, can you find the shortest vector? And that this is very philosophically very similar to the LWE problem in that both give you uniqueness. And in fact, you can show that LWE can be related to the bounded distance decoding problem in the worst case, and bounded distance decoding problem and unique shortest vector are really the same. Right? This is the work of Vadim and maybe Daniele. So uniqueness is the core thing here that you get here, but you don't get in SIS, right? Because SIS seemed like the parameter settings for which the problem was hard was the collision-resistant parameter settings where you have many solutions. Right? And not surprisingly, this will give us public key encryption. Okay, so this is the problem, and M will be large enough to make this solution unique. Okay, so it seems very hard. Let's not dwell on it. I also want to define a variant of the LWE problem, which is the decisional LWE problem, right? It says that so LWE says, given many noisy equations on a secret S, you cannot find S. Decisional LWE says that if I give you many noisy equations, you can't even tell those from just random junk that I threw at you. Right? It's seems like a very strong statement to make, a strong assumption to make. But the interesting thing is that it's not a strong assumption to make. These two things are as hard as each other. This is it's a little bit of an informal statement. It depends on the parameter settings and so on and so forth. But morally, if you can solve decisional LWE, you can solve search LWE. If you can distinguish between these two guys, you can find the secret. Right? So very, very nice statement. Not obvious at all, but that's what it is.
Something about the error now? I mean, what kind of...
No, I don't. No, I don't.
The Gaussian is the same as before, right?
So this statement holds for every error distribution that you can... maybe I need the error distribution to be small enough that I have uniqueness, but that's about it. I mean, it's very sort of agnostic to the error distribution. The catch here, which I didn't tell you, and I'm not going to tell you very much, is that in the reduction, right, you lose some parameters. And what are those parameters? It's the M. There's a number of equations. In other words, if you can solve decisional LWE for something like M equals 100n, let's say, you get 100 times more equations and variables, then I can solve search with a lot more equations. So I'm solving an easier search problem quantitatively than the decision. So that's a little bit of a catch, but I'm really going to set M to be polynomial in M, so I don't care. That's a beautiful, beautiful theorem, and we are going to actually rely on it, black box way. Okay, so that's LWE. Really, I mean, this should, if you do coding theory, this should remind you of something like decoding random linear codes, although we're now working with the Hamming norm. It's a little bit non-standard, in that we are actually adding error that is small in the L2 norm. Learning noisy linear functions, so on and so forth, and it's also related to lattice problems. One way that happens is through a worst case to average case reduction, the same type of thing that we did for SIS. The statement is a little bit harder to sort of say and parse, but essentially what it says is that if you can solve LWE, you can solve sort of gap shortest vector, gap shortest independent vectors problem with related parameters. Okay, so I'm not going to, so there's a quantum version of this reduction, there's a classical version, so it gets a little bit more technical, so this is all I'm going to sort of say about it. Okay, the same kind of worst case to average case you can also do for LWE, essentially. Happy to tell you more offline if you want. Okay, so let's do crypto. Okay, so this, the problem, the hardness of LWE already gives you immediately a one-way function, and in fact even a pseudorandom generator. Right, and what is this function? This is the function, right? By definition, this is a one-way function. And by definition of decisional LWE, this is pseudorandom. So one has to be a little bit careful to ensure that this actually expands. Otherwise, it isn't very meaningful to say pseudorandom, but it does. If you set the error to be small enough, the entropy in the input is larger than smaller than the entropy in the output. So in that sense, it expands. Okay, so one-way function, very easy. Pseudorandom generator, very easy from decisional LWE. Okay. So now let's do a little bit more. Let's do encryption. Okay. So how does encryption work? The secret key is an LWE secret, S, right? And in fact, let's actually start with the secret key encryption, and I'll show you how to make it into a public key in a minute. Okay, so the secret key is a random vector, it's a random LWE secret. How do I encrypt? I pick a random vector A, also in ZQ to the n. I compute the inner product, add the LWE noise to it. So, whatever noise distribution LWE is hard for, pick at random from it, add it. Right? And add the message on top of it. So use this as a one-time pad to XOR with the message. I'm doing something a little bit funky here. I'm not adding the message. I'm adding the message times Q over 2. But really think about it as an error correcting code of the message. Right? So if my message was 0 or 1, which is what I have, and I add a little bit of error to it, you don't know. You can't tell whether it was a 0 or a 1. But if I encoded it this way, and you added a little bit of error, anything smaller than Q over 4 or something like that, you can decode. And so really what's happening here is I am going to use the LWE sample, which is this, as a one-time pad to mask the message, not the message, but the error correcting code of the message. Right? Very straightforward. Just kind of comes out of the definition of LWE. Okay. So why is this secure? Semantic security follows straightforwardly from the hardness of decisional LWE. Why? Because decisional LWE says that this guy is random. So then it's a one-time pad. What are you going to do? Right? That's that. And how do you decrypt? Also straightforward. Once I get the ciphertext and I have the secret key, which is the S, which is the LWE secret. Once I have the secret, I can compute A in a product S, subtract it from here, and what I get is a message, more or less, except it's error correcting code of the message plus some noise. I can decode it, and that's what it is. I get something like M times Q over 2 plus an error, and I can tell whether M was 0 or 1. If it was 0, it's 0 plus a small error. If it's 1, it's Q over 2 plus a small error. I can distinguish. That's that. And so you get correctness as long as the error is not too large. Right. So this error is a mixed bag, right? I mean, you need the guy for security because otherwise it's learning without errors, which isn't particularly hard. But on the other hand, this error, as you will see in Shai's talk, is going to cause a lot of problems. When you do homomorphic operations, you'll end up in big trouble. This is secret key encryption. How do you make this public key? Okay. There are two ways to do it. In fact, they amount to essentially the same thing. There's a devious way and there's a straightforward way. Okay, so let me do the devious way first. Okay, the devious way says this scheme is additively homomorphic. Right? Because if I have an encryption of M and an encryption of M prime, I add them together, I get an encryption of M plus M prime mod 2. Right? With a little bit more error, but between friends, what is an error? Okay, so and I can add a bounded number of these guys. Okay, that's easy. And now let me invoke a beautiful theorem of Rothblum. Again, let me not tell you which Rothblum it is. I'll leave it to you to figure it out. That's my error, right? That's my uncertainty. So, beautiful, beautiful theorem which says that any secret key encryption can be converted into a public encryption. Well, wait a minute. Any secret key homomorphic, additively homomorphic encryption can be converted into a public encryption. Well, here is a secret key additively homomorphic encryption. Done. Okay, let's go home. Right, it's a beautiful, beautiful theorem. And in fact, you would think it is complicated, but it's not even, I mean, it actually preserves the efficiency more or less. It's a very nice theorem. Okay, that's one way to get public encryption. That's not a particularly sort of explicit way to do it, so let me tell you exactly, explicitly how to do it. And in fact, what I'm going to do is an instantiation of Rothblum's theorem. In fact, Rothblum's theorem is a generalization of what I'm going to do. Okay, that's the way things came about. So what is it, right? So I have a secret key, the same as before, no change. Now I have to come up with a public key. What is a public key? A public key is essentially a bunch of LWE samples relative to the secret keys. So namely, a random matrix A together with S transpose A plus an error. Okay. So now you look at it. One way to look at it is that each column of this matrix A together with the corresponding sort of column of B is an encryption of 0 from before. Right? It's a vector A together with S inner product A plus noise, plus 0. So the public key is a bunch of encryptions of 0. That's what it is. Okay. How do I encrypt? I take the public key and multiply it with a random 0-1 vector R. So R, I didn't say it explicitly here, but R is a random 0-1 vector, short vector more generally. So what am I doing here? I'm really taking a bunch of these encryptions of 0 and I'm taking a random linear combination of these guys. Right? And also I have to do the same thing to B, right? I mean, B transpose R plus the message. So that's really what's happening, right? A bunch of encryptions of 0, I take a random linear combination. And that's it. That's the ciphertext. This is a public key encryption algorithm. How do I decrypt? Just look at B transpose R. And that's really, what is B? B is S transpose A plus the error times R is more or less S transpose A times R. Forget the error, right? And S transpose A times R is something I can compute. I have A times R. I have the secret key when I'm decrypting. I can compute this, subtract it from this quantity. I get the message plus the error. I recover the message. Okay, so really so what is the general principle here? To convert a secret key encryption into a public encryption, the public key is a bunch of encryptions of 0. This is more or less what Ron's theorem says. Oh, I gave it away. But more or less, right? So a public key, which is a bunch of encryptions of 0, how do you encrypt? You pick a random linear combination of these encryptions of 0 and add the message to it. Right? Now, of course, by additive homomorphism, this is an encryption of the message, and you can decrypt with the secret key. Right? This is a beautiful, beautiful theorem. I love this. Good. Why do you get security? Right? Security follows from decisional LWE, but that's not quite good enough. You need to argue a little bit more, right? So decisional LWE, for example, says that the public key, if I look at it, what does that look like? Right? It's a bunch of LWE samples. Decisional LWE says that looks random. That really looks like random junk. Now, what am I doing here? Right? I am effectively taking something that looks like random junk and multiplying it with a random 0-1 vector. So the ciphertext is A bearing straight plus 0 and MQ over 2. Right, so this is what the public key looks like. B is random now, so this whole matrix A and B together is totally random. And what am I doing? I'm taking a random matrix, which is public, by the way. It's a random public matrix, and multiplying it with a random secret 0-1 vector. Now you apply left-over-Rush lemma, impliazzo Levin, right? And you get uniformity. So this guy statistically looks random. Right. That's what an instantiation of the left-over-Rush lemma says. You pick a random matrix. You have a vector R that comes from a distribution with entropy, not necessarily random, not random in fact. You do A times R, that gives you uniformly random. Right? As long as things kind of match up, as long as there's enough entropy that I can play with. Right? And that's it. That gives you security. This is a public encryption scheme, and this is Regev's original public encryption system. Yes?
Sorry, just to be clear, is R like a per encryption kind of vector that you're generating?
Indeed it is. It is the randomness that I, every time I generate a fresh R. Yes. Indeed. Any other questions I can answer? Okay, good. So this is public encryption. Okay, so that's that. So we did collision resistance, we did public encryption. I'm getting happier and happier. We'll see how far I get. Okay, so there was a question, in the last talk that I talked about SIS, which is an average case hard problem, LWE, which is another average case problem. What do these things have to do with lattices? Right? Other than the fact that there is a worst case to average case reduction, right? I mean, why are these lattice problems? Okay, well, good question. So let me look at the SIS function. Remember, it was this function that mapped 0, 1 vectors to A times R, mod Q, and this guy is the LWE function. And like I said, this is a surjective function. It compresses many solutions, and this is an injective function for the appropriate parameters. Okay, so what does it have to do with lattices? Okay. So given a matrix A, I can define, there are two ways to define a lattice, at least two ways to define a lattice corresponding to A. One is to say, let me look at the kernel of this matrix, mod Q, right? This is a lattice. It's a discrete space. It's a linear space, and it's a lattice. Right? The set of vectors T. Integer vectors T, I mean, now I'm not going to talk about mod anything, right? So the set of integer vectors T, such that A times T, when I look at it mod Q, rather another way to say this is that A times T is a multiple of, consists of multiples of Q. Right? I look at the set of vectors, take any two such vectors, add them, it is also a vector of this form. 0 is in the set, it's additively closed, and it's discrete, clearly, because these are integer vectors. Any such object is a lattice. Okay, so I didn't tell you this, but what it is. So this is one way to define a lattice, right? This is a kernel lattice or the perp lattice, I'm going to call it. Another way to define a lattice is to say I'm going to take all linear combinations of the rows of A. So these are m-dimensional. So by the way, this is an m-dimensional lattice, right? Because I have A, which is n by m, and T, which is an m-dimensional vector, which is an m-dimensional lattice. This is also an m-dimensional lattice, which is take all linear combinations of the rows of A. This is the image of the linear map A, as opposed to the kernel on the left. And to make this into a lattice, I add essentially QZ to the m to this guy, right? So one way to think about it is that A is A1 up to AN. This is kind of the other way to write it. So what do? I write A1 here, A2 here, and so on and so forth. I populate this. This is an m-dimensional space. And I add Q times all the unit vectors to it. I'm going to also do Q1, A1 plus 2 times A2, which goes here and comes back here, and so on and so forth. And so on and so forth. Right? So essentially, I take the linear space of A. I add all vectors that are multiples of Q to it.
You don't have to say S in ZQ. could be just S and Z.
Yeah, it's the same thing. Yeah, just because I added QZ to the M to it. Right, good point. All right, so these are two lattices, right? This is also a lattice because, again, 0 is in the lattice, it's discrete, it's additively closed, right? It's a lattice. So what is SIS? SIS is exactly the problem of finding short vectors in this lattice, right? So forget about this for a moment. SIS is exactly finding short vectors in the kernel of the lattice. And what is LWE? LWE is a problem of, well, I give you a vector in this lattice plus a little bit of error, decode it back to the original lattice point. It's a bounded distance decoding. We're bounded because I add a little bit of error, right? No more than enough to sort of make the solution unique. Right? So this is why. So both SIS and LWE are lattice problems. One is the short vector problem. I'm not asking for the shortest vector. Just give me one vector whose norm is bounded by something, right? And this is the bounded distance decoding problem. Right? Makes sense? Okay, so it's important to sort of keep this in mind. And we'll get to it in a few minutes.
So is there like a general result which says that if you have, I mean, obviously a lot of these hardness problems they are block parameters you're picking.
Yes. Yes.
So like I think that's what Yevgeny was saying, that when you bring in this mod Q thing,
Yep.
Is there like a general intuition what this Q size has to be, or how is it relating to the?
Good point. So Q really. So a concrete way to ask this question is, how do you pick Q, right? I mean, is Q equals 2 good enough, right? What is the right choice of Q? One way to answer this question is to say, let's run the worst case to average case reduction, right? And whatever Q comes out of it is the right Q, right? So the worst case to average case reduction typically says that Q has to be larger than something, right? Typically polynomial in N. For itized reduction, you need Q to be larger than N, which is the dimension of the lattice. And again, if you run the worst case to average case reduction for LWE, you get something similar. So pick any Q that is larger than a minimum bound, and that's good enough. As opposed to in discrete log, saying that you have to pick Q to be random. Right? You can make an assumption that discrete log is hard for every group of a certain size, but you have to explicitly make that assumption too.
Very quickly, what is the latest? Because things change on this error distribution. We usually swipe it under the rack, and we just right now in the modern technology, do we care if it's uniform, Gaussian, or it's like all equivalent by now?
Good question. So there is a work of Daniele that shows the hardness of LWE for uniform errors from certain range, but it's not completely black box. I mean, there are all sorts of bells and whistles attached to it. So you can show something for uniformly random errors, but I don't think there's a unified framework that says.
So as a user, should we just swipe it under the rack and hope that it doesn't come up in the reduction, or assume Gaussian? I'm just
we will swipe it under the rug, and it won't come up in any of the crypto. In other words, you can start from LWE with any error distribution. You can work with it as long as it is bounded. And the hardness will reduce to LWE with that error distribution. Now the question is, how hard is that? Right? And we run through the worst case to average case reduction too.
Well, just in some applications you use like Gaussian plus Gaussian is another Gaussian, so I'm just trying to see if it's crucial.
We won't, actually. We will be agnostic of the particular distribution of the errors. We'll just use boundedness. In fact, if you look at public key encryption, that's sort of all, right? It uses the fact that the sum of a bunch of error terms is small. So it's true if the error terms themselves are small. This is a great question, by the way. I mean, so characterize the distributions of errors for which LWE is hard, or rather show reductions between different error distributions. I don't think the situation is resolved at all. Yes. So, shall we move on? 15 minutes, which is not nearly enough. Okay, let's see what we can do. Okay, so that's SIS, that's LWE. We went as far as public encryption. Let's move a little bit further. So let's sort of go to our third technique, which is trapdoors for lattices. Again, our starting point is that lattices have many bases: good bases, bad bases, right? I mean, good short and bad is long. What's the point? I mean, I can call a dog a cat, but I mean that doesn't make it a cat, right? I mean, what's the point of labeling these things good and bad, right? Ideally, you want that a good basis lets me do things that a bad basis doesn't. And that's the content of this good and bad business. And what is it that a good basis lets me do that a bad basis doesn't? It turns out this is what it lets me do. Lets me solve the close vector problems, not the closest vector. What it says is, given a basis B and a Y and a point Y in the space in Rm, and is a dimension of the lattice, find me a vector V in the lattice which is close enough to Y. Right? Again, the small is a parameter of the problem. Right? So not necessarily asking you to find the closest vector, asking you to find a vector that is close enough to the point. Okay. I'm going to claim that if you have a short basis, you can solve this problem better than if you have a long, nasty basis. So let's see how to do this. Okay, so this is again a very famous, nice algorithm of Babai. So this is called the Babai rounding algorithm. And how does it work? It works like you expect it to work, in a sense, right? So you have a basis. This is my bad basis, right? I draw the parallelogram for the bad basis. In fact, there are many such parallelograms, right? I mean, if I take this, I kind of shift it here, that's another parallelogram, so on and so forth, and these things tile the lattice, right? First thing I do, I figure out the parallelogram where Y lies. And this is actually pretty easy to do, right? So write Y as a linear combination of the basis vectors, not with integer coefficients because it's not in the lattice, and take the coefficients, round them down. And that gives me the bottom left corner of the parallelepiped. And that's easy to figure out. And now what do? I have a parallelepiped. I know that the guy lives inside the parallelepiped. What do you think I should do? Just make sure that we have enough espresso-filled bodies ready to prove theorems. What would you do? Just round. I mean, what else are you going to do? Right? Just round. What does that mean? You figure out which corner of this parallelogram is closest to this lattice point. And you can do that. You essentially write Y as the basis times a vector, and you round that vector, round the coefficient vector up or down depending on, right? Round it to the nearest corner of the parallelogram, and that's it. You say that is the close vector. Done. Okay, that's the algorithm. Now, the question is, how well does this algorithm do? Okay, so just my pictures are terrible, but let me try to approximate something here. This guy, right, if I look at the parallelogram, the closest point is this green guy. So I'm going to output the green guy as my close vector. Why? Because I'm only looking at the points at the corners of the parallelepiped. The rest of it is immaterial to me, right? That's what the rounding algorithm does. So in other words, the rounding algorithm doesn't see the fact that there is a point outside the parallelogram that's even closer to me than one of the corners of the good basis, of the bad basis. Let me look at another basis. This is another basis, right? Look at the parallelogram. Let me round it, and this is what I get. And in fact, this is a closer vector than this guy, right? I mean, that's the way I picked my picture, but that is in general the case, right? That's what I get. Okay, so where do things stop? How close is this vector as a function of the quality of the basis? Right? So here is something you can show. In fact, it's easy to show. It's a approximately 15-second exercise, right? The distance between the point that the rounding algorithm outputs, which is V, and the point you cared about, y, is at most the sum of the lengths of the basis vectors. Which basis vectors? The basis vectors that you used to round. Not quite that, half of that, but yeah, half. Okay, right? Sum of these things. Why? Because, where did I go? I mean, I rounded to one of the corners of this parallelepiped. The distance is at most the sum of the lengths of the basis vectors times a half, because I only moved half. Right? So that's it. What do you see from this? You see that the quality of the solution here, namely how close is the lattice point to your target point y, depends on how good the basis is, how large the basis vectors are, right? In a very explicit way. You can improve this a little bit by what's called the nearest plane algorithm, also due to Babai, and you can show something like this. If you don't know what this is, don't worry about it. These are the Gram-Schmidt vectors, lengths of the Gram-Schmidt vectors of the basis. Okay, this is slightly better than what's above, but essentially, again, that says here's a measure of the quality of the basis. If it's better in this measure, you get closer vectors. Okay, so what is the moral of the story? The moral says better bases with shorter vectors give you closer vectors. It lets you solve close vector problem better. So that's why a good basis is a good basis, not just because I called it good, right?
No, but it doesn't say that the bad basis is not good, right? Because it can be, it gives just one direction.
Okay, all right. The bad basis is this is a tight connection, right? So if you look at the bad basis, if you look at any basis, in fact, you can find a point where the distance between that and the close vector that the algorithm outputs is something like the sum of the lengths of the basis vectors. It's not quite, right? Because, yeah. Say again?
Is it true on average?
Good question. I want to say yes, but so it's a fraction of points that live very far from inside the parallelepiped that live very far from any lattice point. So as the dimension grows, again, it depends on what the lattice is, but I think that should be true.
Just one quick.
Yes.
It just says that Babai's algorithm performs badly on that basis.
Yeah. No, not at all. I mean, in fact, one cannot hope to say something like that, right? And that is sort of the, yeah. It's just that, there are two things here, right? So one, I'm going to give you a bad basis, right? And I conjecture, I assume that with that, it's hard to solve the close vector problem. And two, I will keep the good basis for myself, and I know that I'm going to solve it better than you, under the assumption, right?
That's all I want to do. It's an assumption. That
Indeed.
Babai's algorithm, in some sense, is the best that you can look at. Because bad bases are being called bad because they are failing in Babai's algorithm measure, in some sense. And you are saying that all adversarial algorithms will fail just because...
Yes. So that's the assumption, right? So really, the content of this is that is that good bases do very well, right? Okay. So here is something that lets me do better and not so much you, right? And that's a trapdoor. Okay. A trapdoor is a good basis. And this, again, this was an idea that you can trace all the way back to the first public encryption of Vaikuntanathan work, and we'll get back to this point in the next 10 minutes. But this is explicitly an idea due to Goldreich, Goldwasser, and Halevi. Okay, again, so what is an idea for if I want to build a trapdoor function? I generate somehow a random lattice plus a good basis, so I come up with them together. And the function is really, something that takes a lattice point as input and noise as input and outputs a noisy lattice point, right? This is, again, very rough. We're going to make it concrete and precise in a slide. The idea, again, is that if you just have the bad basis, if you have just a description of the lattice, it's hard to invert. It's hard to find a close enough vector. But if you had a good basis, you will go back. Right? That's roughly the idea, and that's, in fact, the trapdoor function construction of Shai, Oded, and Shafi. Okay, so the question is, what does it mean? What does it mean, a random lattice? What does it mean, a good basis for this lattice? Right. So that's, I mean, we were struggling with this notion of picking a random point from a lattice. So you have to do something here. So what is a random lattice? For us, we already saw two different kinds of lattices that you can generate, that you can define based on a matrix A, in n by m matrix, right? The lattice and the SIS lattice and the LWE lattice, right? The kernel and the image. And that is what it's going to be. A random lattice is just going to be a random matrix in ZQ to the n by m, right? And that defines two types of lattices, the lambda of A and lambda perp of A. That's what I mean by a random lattice. Okay, and I want a trapdoor, and trapdoor is what? It's a short basis of some lattice. And which lattice is it? I'm going to pick lambda perp of A. Okay, because reasons, I mean, because it has short vectors. So I have to pick something that has short vectors, and that is lambda perp of A. Why? Because remember we said many variables, small number of equations, there are many solutions, likely there is a small one, and this is what it is. Okay, so what is this? What does it mean, a short basis of lambda perp of A? This is a full rank matrix T, so the columns of this matrix are the vectors in the lattice, such that A times T equals 0 mod Q. What does that mean? So look at each column of T. A times a column of T is 0 mod Q, which means that this column lives in the kernel of A. It's a short vector in the kernel of A. Each column of T should have small norm. Right? So the trapdoor is a collection of vectors. Each vector lives in the kernel of A, and each vector is short. And this set of vectors has full rank. Right? That is my notion of a trapdoor, and that is in fact a short basis for this guy, the perp lattice. Okay? Good. It's a little bit, what's this guy doing here? Okay, well, look, I mean, if you think about it, you realize that there is something funky going on here, right? Because A times T, I claim T is what? T is a full rank matrix. It's an m by m matrix, a square matrix. I want A times T to be 0 mod Q, right? It's a full rank matrix, A times T is 0 mod Q. So what could the rank of T be mod Q? And there are several vectors, each row of A, which kill this matrix. Right? The vector times this matrix is 0. So there are several vectors in the kernel of T. So it cannot have full rank. Right? So what am I mean, it seems like there's something, there's a contradiction going on here, right? So I want a full rank matrix, but I also want that A times T is 0 mod Q. What's that gonna? Good. Excellent. So the question is full rank over what? Clearly this matrix cannot be full rank over mod Q because of these two conditions, but it could be full rank over the integers. Right? So something is full rank mod Q means that it's full rank over the integers, not the other way around. Right? In fact, that is what. Okay, so this is very, very important. This is where you, right? One you can get, one doesn't make any sense. Okay, so this is our trapdoor. A bunch of vectors from the kernel of A, short vectors, and they together form a full rank over the integers set. Okay, so not sure what to do exactly, but let me show you what good is this trapdoor. At the very least, I want to show you this, and we'll see where to go from there. Okay. Okay, so I claim that with this notion of trapdoor, if I can somehow generate a random A together with the trapdoor, I can make both the functions that I defined before, namely the SIS function and the LWE function, into trapdoor functions. And they're not just one-way function and pseudorandom generators. All of a sudden we jumped into cryptomania. Right? We get trapdoor functions. Why is that the case? So this is our LWE function, right? And I claim that given the trapdoor for A, the notion that I defined just now, I can invert this function. Okay. How do I do that? Well, I just, have a matrix, I have a vector, what am I going to do? I multiply them, right? I have the output of this function, I have t, multiply them, what do I get? This guy goes to 0, right? The trapdoor is designed to kill this, this A. And what I'm left with is E times t mod q. Right? That's what I get. So now, what would I like, right? I would like to take this E times t mod q and multiply it with t inverse mod q, right? And I get E. And once I get E, subtract it from S transpose A plus E, do Gaussian elimination, you're done. Right? So far, it seems like everything works, but I didn't use the shortness of T. Right? Why is it a short basis? So far, all I said could work, regardless of what this basis was. It cannot, because T doesn't have an inverse mod Q. So you cannot find E. Maybe you can find some linear equations in E, some subspace where E falls, but that's not good enough. And that's where this comes in. Right? E times T mod Q is E times T, because these guys are all small. So mod Q doesn't do me anything. And now I can invert, I can multiply this with the inverse of T over the integers, over rationals, and recover E. And that's it. Right, so this is exactly why, the difference between mod Q, full rank mod Q, and full rank over the integers, really, it's very, absolutely crucial here. Okay, so that's that. Okay, so that gives me an injective trapdoor function. I can also make the SIS function, which is, remember, it's compressing, into a trapdoor function as well. So how do I do that? Well, what's my goal? My goal is I'm given A times Y, A times R, which is B, and R is small, right? My goal is to find this R. What do I do? I start with B. I can compute some Y such that A times Y equals B. I can't sort of jump around in vacuum, right? I have to start somewhere. Here's where I start. A times Y equals B. Y is not necessarily short. So this is something you can find with Gaussian elimination. Right? Nothing really funky going on here. And now I do the following. I find, let me put up one more thing. I look at Y, this is a vector in Z to the M. I look at the lattice, the kernel lattice generated by A, and I find a vector V in the kernel lattice that's close to Y. I use, remember, Babai's rounding algorithm to do this. So what does that mean? And now I say, well, I take this Y, I take the V, the close vector that Babai gave me, subtract them, I claim that is a solution. That's a short vector. That's a short R such that A times R is B mod Q. Right, so why is that the case? First of all, this is short because, thank you, bye-bye, right? This is a close vector, so Y minus V is short. And I claim this is a solution to A times something equals B. Why? Because A times R is the same as A times Y, because A times V is 0. V is in the kernel of A. 0, you get B mod Q. Right, that's it. So really, the problem of inverting the SIS function is exactly the problem of solving the close vector problem. Done. Right? So the same notion of trapdoor makes both the functions, the injective, the SIS function, and the LWE function into trapdoor functions. But there are different kinds of trapdoor functions, right? One is injective, one is surjective, and in a sense they are duals of each other, right? So, and this is actually, one can make this precise. The lattices, the kernel lattice and the image lattice, they are more or less duals of each other.
Does it require any new assumptions? So, it's the same assumptions, it's just information theoretically follows at the gap.
What do you mean? The hardness of this?
The hardness, I guess, is the same assumption.
Yes.
So the fact that you can generate a short, the thing
together. Good. So the thing I haven't told you is how do I generate a lattice A together with the trapdoor? right? And it had better be the case that the A I generate in this way is random. Because otherwise, I cannot, otherwise, why is it hard? Why is this function hard? Right? So I have to generate a random A, which gives me hardness because of SIS, together with a short basis. That's what I have to do.
But in particular, this is an algorithmic thing, but you need to show the existence of, this kind of gap such that, this trapdoor actually works. So that kind of follows from the information, the existence theorem, that a short, right, so you can make an assumption, right, that something is hard to invert if you generate things at random, but the fact that short things kind of exist is just by counting, or?
The fact that short vectors and short solutions exist is either by counting or by Minkowski's, essentially counting. Right? Minkowski's counting. Good, so you get two, at the price of one, you get two trapdoor functions. Okay, so, all right, so, let's see how to go from here.
Let's discuss it.
I'm open to discussion.
Okay. How much?
How much do you pay?
Okay. Yeah. So I want to show at least one thing, right? Which is not so much to. I want to show one thing, which is how much does 5 minutes cost?
5 for free.
Okay, you know what? Let me actually get to it without talking, right? Okay, so what I want to show is how to generate a random lattice together with one vector in the kernel, one short vector in the kernel. Now, if you have one, you get two, you get three, we get everything. Okay, so it's not quite true. This is where the heart of the difficulty lies, but I won't get to it. Again, if you want to do crypto, all you have to know is that there exists a way to sample this with this. Okay, so let's do the warm-up, and that'll be it. Right, so this is essentially a technique that goes all the way back to Itai's work, and it's also comes up in the work of Itai and Dwork. And this is a way to generate a random A with one short vector. How would you do it? Right? I cannot start from a random A and hope to find a short vector. It's actually hard. So I have to do both at the same time. How do I do it? I pick an A prime, which is the same as the A, except it is missing one column at the very end. Right? It's m minus 1 columns. So this is part of my A, part of my instance. And I pick R, which is a random 0, 1 vector. Again, of length m minus 1. This is my solution. So I constructed part of my instance, and I constructed a solution. And now I'm going to complete it. Right? So I'm going to define my lattice A, that's my instance, to be A prime with another column, which is A prime times R, essentially, more or less. Right? Minus A prime times R. And what is the vector that I get out of it? What is the trapdoor vector? By doing this, I got for free a vector in the kernel of this lattice, which is R and 1. If you multiply the two, you get 0, mod q. It's a beautiful technique, very simple, but it's really nice. Okay, so I have to show many things. I have to show that A that I constructed this way is close to random, and that's by leftover hash lemma. This was random to begin with, and this was essentially a random matrix times a 0, 1 vector, a random 0, 1 vector. And as long as this guy has enough entropy, you get uniformity. That you do by fixing parameters. Right? As long as you have this guarantee, you're done. A times R is 0 mod q. So A times T is 0 mod q. Sorry. And T has small norm, because each entry of R is either 0 or 1. So how large can it be? Square root of m. Done. That's it. Now, if I can do 1, why can't I do 2? Right? I pick not sort of one column less, a matrix that's one column less, but 2 columns less. And I pick one vector that gives me one thing that gives me one trapdoor vector. I give another thing that gives me another trapdoor vector. Unfortunately, life is not that easy, because every time I pick a new trapdoor vector, I'm adding one column to the matrix. So I say 1, I get 1, I say 2, I get 2, 3, I get 3. I'm never going to get as many trapdoor vectors as the number of columns of A. Never going to happen. Right? I'm never going to get a trapdoor for full basis. We saw that unless you have a full basis, I'm in trouble. What does inverse mean? How do I invert these functions? Right? So this is something that you have to solve. This is really the major sort of idea in a work of Aitai from '99, considerably simplified over the years, and so the state of the art is a work of Michancho and Paikut, which is 2 slides, but unless I pay Tal a deuce, I don't get 2 slides. Right? So really, I'm somewhat happy because I told you what these things are, not so much how I get the trapdoors, but you don't have to know, right? I mean, what you don't know won't hurt you. So on and so forth. It's all very, very nice and simple. Clearly. Okay, so at least I have to tell you one open question, right? I mean, what is a talk without an open question? So here's the thing. I showed you 2 kinds of trapdoor functions. Okay, one is an injective trapdoor function, but it's actually an expanding function, right? It's the LWE function. And I showed you a compressing function, which is a many-to-one, by definition a many-to-one function. It's actually a surjective function as well. Right? It's a bit like, what do you say in English? Have your cake and eat it, right? I mean, can you get one function that is both injective and surjective? In other words, can you get a trapdoor permutation from lattices? Right? And if you get a trapdoor permutation, you get all sorts of nice things. And I'm not asking this question. There are certain questions you can ask for the sake of asking it, right? And I claim this is not such a question. There's something very deep going on here, which is, where does the hardness of these lattice problems come from? They come from the fact that you have these noise terms, right? I mean, you have something that is not exact. You destroy structure to get hardness. And the question of trapdoor permutations really asks, can you get perfect structure from some assumption that is inherently noisy?
Right? Is it open to do one-way permutations?
Yes, indeed. So forget trapdoor. One-way permutations is already, we don't know. Right, so this I think, and IZK proofs, which will follow from trapdoor permutations, this is something that has haunted me for, I don't know, like 7 years, 8 years, since I started working on lattices. And if someone puts me out of my misery, I'll be very happy. In fact, I was tempted to kind of put money down on the stage, in front of the camera, but I'll resist. $100 for the guy who, not eventually, have to do with a bounded time, 2 years. Okay, so 2 years, give me a trapdoor permutation. In fact, forget it. Just give me an NIZK proof for all of NP.
Heuristic constructions from lattices using I/O, right? You can obfuscate.
Okay, so this, so you know what? Just to avoid, giving you $100 of my hard-earned cash, let me make it harder. Okay, so I want trapdoor permutations from a worst-case hardness assumption on lattices. That's not a very high bar, right? And that's what I want. And that you can pick ideal lattices if you want. You can work with ideal lattices, but it has to be something with the worst-case to average-case reduction. Even better, if you construct something from LWE, it's best of all, very, very happy. Okay, so I think this is way too much.
Thank you. Go to the thank you slide.
This is it. This is thank you. I did all these things.